So the topic is Steinitz lemma, and I'll tell you what it says. And anybody knows what it says? Very good. Good audience.
Oh, I think I knew. Once I knew.
Yeah. This is a repetition.
Abstract to the same.
So it is, V is a subset of B, which is in RD, unit mole of some norm, finite, and has the property that the sum of the vectors in V is 0. So this is the condition. So if you imagine, here is a point, the origin, you start up with the first vector, second vector, third vector, etc. You zigzag around, and you come back here in the end. Of course, you can make it large, because if you, for instance, order the vectors by slope, then you get a big convex polygon, right? In any dimension. The question is just the opposite. Can you reorder them so that every partial sum remains in a small ball? Can you? You can't make it arbitrarily small, but how small can you make it? This is the question. And theorem by Steinitz in 1913 says that indeed there is an ordering V equals V1 to Vn such that the maximum of the sums from 1 to k over k Vi norm is smaller than a constant that only depends on the norm. Right?
Independent of n.
Independent of n. I will be more specific about what this constant is, but let's agree that it is a constant which depends on the unit ball, the norm, and let's call it the Steinitz constant. Right? And I will give two proofs of this one. One is a bad proof. It's a good proof, but and the second one is much more better. The first one is starts with the case B equals 1, which is very simple, right? You have real numbers that sum to 0, and all of them is at most 1 in absolute value. Then you start using the positive ones. Before you would pass over 1, you start using the negative ones, and so on, you zigzag. So for the constant here is just one dimension is 1. And assume that the constant in is CD minus 1 in dimension D minus 1. And then do the following. I have this vectors, set of vectors here. And I choose a subset, say W, such that the sum of the vectors in U has norm maximal among all subsets. Right? So I try to choose as many vectors as I can so that I go far away from the origin. Let's call this number here A, vector here A. Right? So the picture is this one. Here is a vector A. Here is the origin. Here is the orthogonal complement of the subspace. I notice immediately that negative A is also a maximal vector because your complementary set has the same property. Right?
And the sum is 0.
The sum is 0, but here the sum is not 0. The sum is 0, that's why the opposite, the complementary set has some minus A. This is what you said.
Yes.
Yeah, absolutely right. So this is again, and I also notice that any set in this maximal subset has a non-negative component in the direction A. Also, non-negative components in the direction A. If it had one with negative coefficient, then I would add it here, and I would go farther away from the origin. right? So everybody in V has positive non-negative component in this direction, a negative component in this direction in the complementary. Very good. So you look at this is Rd minus 1, and the projection of all vectors is in the unit ball of d minus 1, and the sum to 0. So I can use the induction hypothesis, and it results in a broken line using the vectors only in U from 0 to A, and I can do the same thing in the complementars W. And every partial sum here is smaller than CD minus 1. And same happens here in this direction. Again, I have an ordering in which every partial sum is smaller than CD minus 1. Now I borrow the argument from here. I start using the vectors from this one, and as soon as I would pass level 1, this is one from this plane, I start using those. And then just I go up and down between minus 1 and 1 in this direction. So what I get is always a vector whose A component is at most 1, and the complementary component is at most twice CD minus 1. So CD squared is smaller than 4 CD minus 1 squared plus 1. So this is a recursion which you can compute. It's slightly larger than doubling, right? But it's exponential indeed. So you get an exponential amount for the Euclidean ball from here, or norm. So this is the bad proof. It's a nice proof, right?
It's a nice proof.
There is no problem with that. But I give a better proof. And I remove this part from here. Instead of creating an ordering, I create something different. And something different is the following. I create a system of subsets V equals Vn, subset Vn minus 1, subset Vd. So this is a sequence of subsets. V sub k has exactly k elements, right? And with and I also construct a alpha k, a mapping from Vk to 0, 1, right? Which is a linear dependence of the vectors in this set. So satisfy sum V in V sub k, alpha k V times V equals 0. So this is just a linear dependence. And one more condition, the sum of the alpha k V in Vk is equal to k minus d. So this is what I want to construct, such a linear dependence on backward induction on n. Okay. So for Vn, we have such a thing, right? Because I have the O1 linear combination, O1 coefficients, and if I divide n, instead of 1, I write n minus d over n, then I get this number here and 0 over there. Right? So with n equals 1 and k equals n, we are done. So our next move is from k to k plus 1. No, from k to k minus 1. Because I go downhill. And for that one, I start with an auxiliary system, linear system. And the auxiliary system is this one, sum of beta v is 0 with v in v sub k, and sum of beta v is equal to k minus 1 minus d, v in vk. So this is almost the same as here, but the target is one smaller, right? This one has a solution, because the previous solution multiplied by k minus 1 minus d over k minus d is a solution here as well, automatically. So this one has a solution. Solution. Of course, every beta is between 0 and 1. I did not write it up here. Now I need your help. We go to an extreme point. It's a polytope, right? It's in the cube intersected by a hyperplane or a plane. So this set of betas is a polytope. It has an extremal vertex. An extremal vertex. At an extremal vertex, how many inequalities have to be satisfied by inequalities? Let me write down the inequalities. Still less than 1 for every v. So I have altogether k variables, d plus 1 equations. So k minus d minus 1 times equality holds either here or here altogether. I want to claim that there is one beta for which this is 0. Right? I claim that there is one beta for this which is 0. So if everybody is here, then I have this many ones, so the sum is already done, and I have a few more variables that are all positive. So I overshoot. So there is an extreme ray, and there is a beta star, where beta star v star is equal to 0. And what I do next? I just drop it from vk. So then I define vk minus 1 equals vk v star set out, and alpha k equals this beta star. Right? Very good. Right? And now there is an ordering, because here is I use a different color. There is a vector vn here between these two, which I deleted, vn minus 1, and here is a vd plus 1. And this is going to be my ordering, except the last d vectors that I order arbitrarily. Doesn't matter. So I get an ordering v1, v2, etc. And I want to check the sum from 1 to k v sub I. And I want to say that its norm is small. And I claim the norm is smaller than dimension. I claim that the norm is smaller than dimension. So this is trivial if k is smaller than or equal to d. Right? Because the vectors have shorter length than 1, so that the total sum. So if k is larger, then I simply subtract from this one some alpha k v in vk. This is the same set. Right? So this is equal to sum 1 minus alpha kv times v in vk. And I'm done again, because the norm of this one is smaller than the absolute value of this one, which is just the value of this one, times 1, because the absolute value of the norm of this one is 1. So this is, in the norm, this is smaller than the sum of 1 minus alpha kv, v in vk. So this gives you k, and this gives you k minus d. By the prescription here. So this is equal to d. So it tells you that this Steinitz constant is always smaller than or equal to D. Is this a better proof than the previous one?
Slick. Very slick.
It's very nice proof, right? Very elegant proof. This proof is due to Greenberg and Sebastianov in 1980 or 1979. And actually, Steinitz in 1913 proved the same thing with twice D. And with a similar method, linear algebra basically, but his paper is something like, it's in 3 parts, and it's about 100 pages long. It's in German. I tried to read it. It's not so easy. He also struggles because he said, instead of an affine subspace, he said, lineare Mannigfaltigkeiten. So he has to invent things that were probably known but did not have a proper name. Actually, in this paper, he proves his Steinitz lemma, another Steinitz lemma, saying that if a point is in the interior of the convex half of a set of points, then it is in the interior of at most 2D of those vectors. So that's how the 2D comes in this case, I think. I want to mention that this is Greenberg Sebastianov. And Sebastianov. I proved the same thing about the same time with 1.5D, with a linear algebra method, but different. So this is the Steinitz lemma.
Imre, there's also, I think, Steinitz also, I think, proved as a result about the convergent set of...
Yeah, this is what I want to talk about next.
Oh, okay.
Yeah. So the whole question was motivated by a question of Riemann. Riemann proved that if you have a conditional convergent series of real numbers, then by rearrangement you can make it converge to any number in the unit on the line. So if and his question was, what is the set of points that you can make a series of vectors to converge by rearrangements? So this is the motivating question. This is and soon you understand that this is the main obstacle. Steinitz lemma is needed. For instance, if you have a system of subsets of your series, increasing subsets, whose sum tends to a certain vector, then you can find a ordering of the vectors using these slices or partial sums. You only have to care about what happens between two partial sums that are close to the target point. And then these vectors are all short, and you can rearrange them in a I will come back to the 2 version of that one, but you understand that if, yeah. So this is the crucial step in that proof. And this was also understood by Levy, who proved the same theorem in 1904 in the planar case. And actually, Steinitz starts by saying that he had thought that Herr Levy proved the thing in full generality, but he realized that it was only in 2 dimensions. That's why he publishes his result. So yeah. So and there is a huge literature about this question of Riemann, and this theorem answers that the set of points you can make a vector series converge to by rearrangement is an affine subspace, meaning either the empty set or a single point or a line or a plane or the whole space, etc. A beautiful result in itself. There is a direction in analysis to understand what is the case with other spaces. This is the Euclidean space, and you look at the function spaces or some other spaces, and what is the set of points you can make a series converge by rearrangement. And I know a little bit about those results, but not much. And I don't want to talk about that much.
Is it very different then? Or
Pardon me?
are the results then very different? The results, are they very different
In some cases, this is not true.
Yes.
In some cases, it's not a affine subspace.
Okay.
Depends on, you are familiar with this
If
one.
I remember it correctly, Kaditz and Kaditz gave an example of a Banach space and a series where the rearrangements converge to 2 points.
Oh, okay, yes.
And proved that there is no example where it converged to 3 points.
Yeah, this type of results. Yeah.
Yeah, we don't want that.
But in that space, this Steinitz lemma must miss underneath it. I mentioned already the two version, and the two version is that the sum is not 0 but a certain vector A, and then you can rearrange your system so that the kth partial sum differs from k over n times A by at most twice d. So this is automatic almost, because you subtract from each vector the 1 over n times the A, the sum vector, then you get vectors whose length is at most 2, and they sum to 0 and apply the theorem. And so I hope that's sufficient to say. Yeah. So, questions. What is this? What is the value here in general? So this is a good bar, D. But is it the best? Well, it is the best in one sense. Namely, there is a norm for which you can't beat D. Namely, this is a non-symmetric norm. Take say the regular simplex in D dimensions with center at the origin and unit vectors. And consider this simplex the unit ball of your space. Then the sum of the vectors is 0, but if you take all but 1, then they sum to minus d times the other vector. And so that's possible actually for symmetric norms. Slightly better result is not d minus 1 plus 1 over d. So in dimension 2, for every norm, every symmetric norm, 1.5 times d is true as well. And you can modify this proof a little and then get it. But what is the value of S of B for some other things? L1 norm, you can check that it is at least d half. So in L1 norm is the order of magnitude is okay. For L2 norm, SL2, is larger than square root of dimension over 2 by, say, using the standard unit vectors. This is d vectors, and 1 over d times the sum times minus 1, again d times. And if you go halfway up, then you can see that the unit, the L1 norm of the sum is at least this. No, the L2 norm of the sum is at least this one. And S of L infinity is also square root of d over 4. This is not quite precise. And you prove it by using Adamar matrices and making the first row equal 1. Every component in the first row equal 1. Then the remainders of the columns sum to 0, right? Because the multiplied by the first, so 0, and then you try to rearrange them, and it's almost an orthonormal system in one dimension lower. And then you get, but it works only when there is an Adamar matrix, and so you have to fight a little bit more for this one. But there is a general question that this is smaller than O square root of D. Right? But nothing is known about that. Nothing is known about that. Not even that any one of them is smaller than D over 3. So not just little of D is not known, but D over 5 is not known. Moreover, there is no norm for which you would know the D over 10. So there are many questions around here. Right, so question 1. Upper bounds here, upper bounds here. Actually, in dimension 3, in dimension 2, this is known to be square root of 5 over 2. And yeah, so this result has, so I mentioned you the Riemann's question, and there are many other applications, and I want to explain you a few of those. The first is a fairly recent application by Eisendrath and Weismantel concerning integer programming. And I will not explain it in full detail, but I try to explain the essence of it. So you have a times x equal to b. A is n by m by n integral matrix. Then B is a Rm, this is M root Rm, integer vector, and x is larger than or equal to 0. The integer programming, you want to have x an integer, right? And the question is whether this system is feasible. And one more condition, you assume that Aij is, this is the number smaller than, say, delta for every I and j. So this is the coefficients are not too big. Right, and I want to try to treat feasibility of this problem. Assume it is feasible, which means that there is a solution x equals x1, xn, right? Yeah. And write a1, an for the columns of A. This simply means that x1 times a1 plus x2 times a2 plus etc. is equal to b, and all the x's are non-negative integers. Right? I can write it this way: a1 plus a1 x1 times plus a2 x2 times plus an xn times, and this is 0. This is equal to b, not 0, b. This is a total number of t equals sum 1 to n xi vectors that sum to b. So there is a rearrangement of these vectors along which the all partial sum remain in the tube. What is the tube? It is the origin is here, b is somewhere here, and then you take the delta box around this one and around this one. I mean the d times delta box around this one, and you know that the along this ordering, the vectors from here go, etc., and end up here. Right? Now you define a directed graph whose vertices are the integer points in this tube. And two connected, if A and not A and B, U and V are connected, if U minus V is a column of your matrix. So this is a possible move from here to here by A sub I, right? And then this is a directed graph with no number of vertices, with no number of edges, and the question is whether there is a directed path from the origin to B in this graph. So that it's feasible if and only if there is a directed path in this directed graph G. So this is the basic idea of Heisenberg and Weismantel, and they establish theorem saying that you can decide according to an algorithm whether there is a directed path in your graph or not, and then you get a better one than previously known. And since then, this has become a sort of industry. So many results come this way. This is a nice application, right?
This means that you are able to so if you give me V1 up to Vn, then you can really say which is the first vector, which is the second one.
Yeah.
So this is an existence proof that there is a rearrangement, but you have to know the rearrangement here. There must be an algorithm giving you the rearrangement.
So that proof is algorithmic.
Yeah.
So you can do it with an algorithm, and in this case you don't know the vectors x1, xn. So you can't a priori order the vectors so that they sum to, that they stay in. But if there is one, then there is one which is a directed path in this graph. And that directed path can be found by a graph algorithm. Right? So you can't use that algorithm because the x are unknown. But you can use this graph algorithm to find the xi's, and then once you know the xi's, how many steps you make in direction A1, then you know the solution. So this comes from a different, the existence is used here.
Okay, you have a look at all graphs which may occur, and then there's one which satisfies or not.
You look at all possible paths, but there are paths finding the shortest path normally in a directed graph. You have to make sure that there is no zero loop. Something like that is needed. So this was one application. Another application is Lyapunov's theorem on vector-valued measures.
So this this algorithm is basically this Steinitz result. Or,
Yes,
this algorithm you need there.
yes.
This is basically this result of Steinitz, or
No. This is a graph theory thing, right? This is a directed graph, fully described. I know how many vertices are there.
yes.
I know what are the edges, how many edges are there. And so this is a directed graph. I forget about the vectors, anything you like. And there is an algorithm to decide whether there is a directed path from point A to point B in a directed graph. And this algorithm has a certain complexity. I mean, how many steps you take.
Okay.
And that gives you, by that algorithm, you can decide whether there is a directed path in this graph without Steinitz theorem. The Steinitz theorem is used in order to locate this directed graph.
So it gives you the width of the tube.
Yeah, because if you want to find a solution to the system is a certain, so if there is a zigzag using positive steps with AIs that reach from here to here, but any zigzag can be arbitrarily far away. This Steinitz lemma restricts your attention to a smaller set. So this is the advantage of the existence part. Also, because the blow-up factor is at most dimension, there are not too many points in here. So d to the d points are unavoidable because in this box there are actually 2d to the d points in there.
Can you say something about this algorithm?
The shortest path algorithm.
Oh, okay.
I taught it in London a few times. I can record it for next time. I don't. It's not. So basically, you start with a set, and then you look at the edges going out from here, and their endpoints can be reached in one step, right? And now you look at the vertices here, and you look at the edges going out from here, and this is another set, and I don't include this one if there is a backward edge over there. So this is what you can reach in one step, this is what you can reach in the second step. So from here, you choose all the outgoing edges. This is the next one. And whenever it reaches your point, target point, then you have a... So there is more, it's normally more sophisticated than that. But this is the basic observation. And it is shortest paths in graphs were figured out in the 30s. And then again in the 50s, different people. So Czechs call it Borůvka's algorithm because the Czech called Borůvka discovered this shortest path. And then it was when, Lyapunov's theorem about vector measures. So if you look at the ordinary measure, which is non-atomic, and the values it can take is an interval. Bounded or infinite, doesn't matter. What happens if you look at a vector measure? So every Oertel set is associated with a vector. And this vector satisfies the usual measure conditions. What is the set of points that can be the value of a vector measure? Well, if there is an atom, positive measure atom, that you may jump. So everything is small, and when you include this point, this is just So, but Lyapunov theorem says that No, for a non-atomic measure, it is always a complex set. And he uses Steinitz lemma for the proof. I don't go into details, but I want to mention another application. There is another quite spectacular application that I want to explain, and this is in scheduling. I tell you what scheduling, flow shop scheduling is. Flow shop scheduling. So there are M machines and N jobs. You should think of this one, say you have 1,000 pieces of wood, right? And you have to cut it up by a saw into smaller pieces. Then you have to drill a hole in every one of them at different places. Then you have to polish it, and then you have to paint it. So this is 4 machines. And of course you start with an object, then you finish with that object on that machine without interruption, and then it can go to the second machine, right? Unless the second machine is occupied at that moment, etc. And so this is what happens here. So this is machine J on job I takes Tij time. Good. And this is how it looks. So this is the first machine, second machine, third machine, fourth machine, and then you take the first job starts on the first machine and takes up this much time, and it starts on the second machine and takes up this time, and then it comes to the third, it takes up this time, and then it takes up this time. And then comes the second job and goes to this machine and stops here, but you can't continue on the second machine because it's occupied. So you go over here, and this is your second machine. You should start here because it's not occupied, but you are on a different machine. It takes this much, and then this is the next one. And
the ordering of the machines is different.
Pardon me?
The ordering of the machines, you start with the first machine and the second. So
this is fixed, like the piece of wood. You can't paint before cutting it up. So this is the condition. So that there are red jobs coming from here to here, here to here, here to here, etc. And there is a moment when everything finishes on the last machine, which is the last machine, and this is called T final. And your target is to minimize this final time, right? So this is the problem. It's not to be NP-complete, so there is no hope for an optimal solution. So what I'm going to give is a approximate solution. And the algorithm uses Steinitz theorem. And I assume that this number here is smaller than, say, a constant for every I and j. So there is not too big. And I write T sub I, T sub j equals the sum of T, Eij, I equals 1 to n for the time necessary on the jth machine. The total time spent on the jobs. And I write T naught equals the maximum of T of j. And this is definitely a lower bound on T final. Right? Because you can't. And I'm going to give an algorithm that finds an ordering of the jobs so that the T final is not much bigger than the optimal solution. And the not much bigger is going to be something like optimal plus m squared times c, which means that it does not depend on the number of jobs, it depends on the number of machines and on the bound on c. So this is what I'm going to do. And first I assume that everybody is equal to t naught. This is a very strict condition, right? I just assume that the total sum of the jobs in every machine is the same. But that's no problem, because I introduce dummy jobs whose length is at most c.
It's happening all the time.
And I include them in the system. And the machine will be idle on a dummy job, but I keep the sum the same, right? And then I take the i's job I, and associate it with the vector t I1 minus t I2, t I2 minus t I3, t I m minus 1 minus t I m. This is a vector in c times unit ball of m minus 1 maximum norm. Right? Every guy here is at most c, so the difference is at most c. Everybody is positive, so this is over there, and the sum is equal to 0. Right? That I made them to be equal to 0. So that there is an ordering of the vectors, so that every partial sum is small. Right? So if I translate it back to this picture, in this other picture, what is the partial sum here? The partial sum is, for instance, this component is sum t I2 minus t I3, I equals 1 to k, which is sum t I2 from 1 to k minus sum t to k t I3. So this is the completion time of the first k jobs on the second machine. Right, this is somewhere here. And this is the completion time of the first k jobs on the third machine, which is somewhere here, and the difference is not too big. Right? So this machine is finished here, and this one is finished here. And so here is the next one comes here, and the next one comes here. And they are close to each other, and I want them to be, maybe a better picture, it is here and this is here. So then I can't do anything because they are too close to each other. What shall I do? I just push up. So this is this green job, and this is the green job here, and this is the green job here. Somewhere, they ended up somewhere here. I will not go into the exact details, but I tell you what to do. So I know that this one differs from this one by at most c times m minus 1. Once more, this number and this number differ from each other by at most c m minus 1. Then I push this block up here by c m minus 1. So everything that is here, I push up. There will be an empty slot here, Cm minus 1 plus C, and then this guy moves up here. So this is the new job, and the end point of this one is before the beginning of this one, because the difference was Cm minus 1 between this one and this one. Here is at most m, at most c. So And so I push this line up by 2 times as much. So this is going to be, this job is going to be here. And again, it starts when it is finished in that one. And you push up the last one by this amount as well. So you have to push up C times Cm each time, and whatever C times M minus 1, because M minus 1 pushing up and over there. I think this, so this is the end of the story. I did not formulate it as a theorem, but what I found schedule with P final than P optimal plus C times M minus 1. So this is, and this can be found in polynomial time, because this algorithm here is polynomial time algorithm for the vectors. Especially when M is 1000 and the M is 4 and the number of jobs is 1000, this is a good solution. So I can finish any moment, huh? Right?
Okay.
I can continue.
Continue like in a little bit longer. Yeah, but we still want next week.
What I want to say is that this Steinitz lemma has millions of applications, various applications. I give you Riemann, the integer programming, this one, Lyapunov. I can give you one more in a moment. There is a collection of articles concerning Steinitz lemma and the balancing vector problem, which comes next, and which from 1982, listing something like 220 papers. Since then, there are many more. And there are plenty of applications in various directions. So I can't mention them all. Maybe instead of giving one more application, I tell you balancing vector result and the problem, okay? So balancing vectors, actually it started with Dvoretsky in 1960 or 3, I think. But what the example I want to give you is a game invented by George Spencer. In the game there is a pusher and a chooser. And what happens is that pusher chooses a Euclidean unit vector and tells it, say V1, tells it to chooser. The chooser chooses epsilon 1 equals plus or minus 1. And then in the next round, pusher chooses a vector V2 and he then chooses epsilon 2, etc. And the position of the game after n steps is sum 1 to n epsilon I vi. And the name suggests that the pusher wants this point to be as far from the origin as possible. And the chooser wants to keep it as close to the origin as possible. And this is a very simple game. And I tell you why. Because if the current position is this one, then the pusher chooses a vector orthogonal to this one. Right? A unit vector orthogonal to this one. So the length of the new vector will be square root of length of this one squared plus 1. So this means that the value is square root of n. This is what pusher can guarantee by choosing always an orthogonal vector. And chooser can guarantee the same thing. Namely, at every point, whatever he gets, he chooses the smallest of the two options, shortest of the two This is again square root of n. This is a balancing game. Of course, you can ask it with the maximum norm, etc. I want to give you an open question, which Greenberg sent me 6 years ago in an email letter, and Greenberg died something like 4 years ago, and I discovered his letter in my letterbox with this question. He says, what if Pusher is limited? So Pusher can choose any vector from the unit circle. And what if he can only choose these vectors here? And of course the opposite vectors, which is the same. So what is the value of the game in that case? Certainly smaller than square root of n, because chooser can use the same strategy. I could prove that Pusher has a strategy giving more than 0.4142 square root of n, square root of 2 times minus 1, square root of 2 minus 1 times square root of n, but I could not prove that you can do better than 0.99 square root of n for Pusher. I don't know the answer. So this is a balancing game, and I offer you to work on this one. What I could prove is that if you take a different norm, maybe this norm, say, this is a quarter of a circle, this is a quarter of a circle, then the Pusher can reach that this point is outside square root of 2 times a certain factor of this one, and chooser can make sure that it is in a slightly larger copy of this one, a point. But the two numbers don't agree, and this is the square root of 2 minus 1, the length here, and that gives me the lower bound for this modified problem. So I leave you with this problem for next week. And solutions are welcome.
Thank you. Thank you.